final application of double integrals that we're going to look at is going to be the surface area of a three-dimensional object. So let's consider we have a surface, it's continuous, and one of the ways that we're able to find the surface area is to be able to break the surface into a number of different tangent vector parallelograms. So let's say we have a point that exists somewhere on the surface. And what we can do is we can find the tangent vector in the x direction and the tangent vector in the y direction. And what we can do is we can construct a parallelogram out of those tangent vectors. So let's call this vector A, and let's call this vector B. And you recall that being able to find the area of a parallelogram with vectors, you can just take the cross product. And that's exactly what we're going to do, is we're going to find the tangent vector, and we're going to be able to find the cross product of that. If we do so, we're going to get this form. And that form can be rewritten as a derivative. So we're going to factor out the delta x, delta y, and that's just going to represent the delta A in two dimensions, or in the xy plane. Now that can be turned into a double Riemann sum. So we're going to take this magnitude, we're going to add up all of the different surface areas from those tangent vectors and the cross products of those, and eventually what we're going to end up with is the double integral of the derivative with respect to x squared, the derivative with respect to y squared plus 1. What you'll notice is this looks very much like what we saw in Calc 2, except in Calc 2 you probably only had that because you were only working in 2 dimensions. However, in Calc 3, since we're dealing with 3 dimensions, now we're going to just throw in that fy of x. So now that we know the formula, let's go ahead and look at an example. We want to find the surface area of the part of this surface, z equals x plus y squared, that lies above the triangle in the xy plane with vertices 0, 0, 1, 0, and 0, 1. Let's construct that area first. The point 0, 0 is the origin, the point 1, 1, and then finally the point 0, 1. So we have a triangular region that looks like this. We have the equations y equals 1 for the upper bound. We have x equals 0 for the lower bound on the left side. And then if we were to go through and use the equation of a line, we would very easily see that the slant, the 45-degree angle is y equals x. We're going to later learn if it's a type 1 or type 2 region. In fact, in this case, it could be either. The other thing we want to do, we want to find fx, which is 1. We want to find fy, which is 2y. And our function that we're dealing with is this z equals x plus y squared. Right? So we just find the derivative of that function with respect to both x and y. Now we're going to set up the double integral, but we're not going to set up the bounds, and I'll describe why we don't do that yet. Double integral of sum area A, square root of 1 square plus 2y square plus 1 dA. Right? So this is fx square, and then we have fy, or f sub y square, excuse me, and f sub x square, and then we have the 1. All right, so remember, that's our formula for surface area that we just found previously. If we simplify that just a little bit, we're going to end up with the double area, or the double integral of the area of 4y squared plus 2 dA. Now's the time to consider whether you want it to be a type 1 or a type 2 integral. Notice that this would be a very rigorous integral to define or to try to evaluate with respect to y. Okay, so if it was a type 1, we would need a trig sum. Okay, and remember, type 1 is the one that has dy dx as the ordering. We want to try to avoid that if at all possible. So let's try it as a type 2 region to start with. And then if that doesn't work, then we can go back to the trig sub. We're going to see that it does work nicely. All right, so we go back up. We're going left to right because we want it to be a type 2 integral. Notice that x is going to range from 0 to x to y, and then y is going to range from 0 to 1. Okay, so 0 is less than or equal to x, which is less than or equal to y, and then 0 is less than or equal to y, which is less than or equal to 1. So our double integral is going to be 0 to 1, 0 to x, square root 4y squared plus 2, and then we're going to have dx dy. Fortunately, there are no x's whatsoever in the original integrand, so this makes it really easy. Oh, excuse me. This is going to range, I goofed the bound, so this is going to be 0 to y. There we go. So this makes it really easy to evaluate at this point. So now we're going to have, let's just evaluate in terms of x. So that's going to be 0 to 1. Antiderivative of root 4y squared plus 2 with respect to x is just going to be x. That's going to range from 0 to y of root 4y squared plus 2. We still have the dy. If we substitute 0, 0 goes away. If we substitute y, we just get y. So this is just going to become the integral from 0 to 1 of y root 4y squared plus 2 dy. And the good news is now this is just a trig sub. All right. I'm sorry, a u substitution. In the other one, it would have been a trig substitution. So u 4y squared plus 2 du over 8 is going to be y dy. All right. So verify that for yourself. So now we're going to rewrite the integral just in terms of u. So now this is going to be a to b square root of u du over 8. All right, now we're starting to see that this is a fairly easy integral. We're going to now rewrite this so we can set it up. So as a setup, 1/8 a to b u to the 1/2 du. We're going to add 1, divide by the new exponent. So 1/8 u to the 3/2 divided by 3/2 a to b. Multiplying by the reciprocal, that becomes 2 over 24 or 1/12. We're going to back substitute. So now it becomes the square root of 4y squared plus 2 cubed, 2/3 or 3/2 power, and that's going to range now from 0 to 1. We can't ignore 0. 0 does have significance in the problem because it's not going to be a polynomial expression. All right, so this now becomes 1/12 the square root of 4 times 1 squared plus 2 cubed. Then we're going to substitute 0 back in there. So minus 1/12 square root of quantity 4 times 0 squared plus 2 cubed. At this point, we can simplify underneath the radicals. So we get 4 plus 2, which is 6. 6 to the 3rd is 216. So we get 1/12 root 216 minus 1/12 root of 2 cubed is 8. If you want to leave it like that, that's fine. Another way to write this is 1/12 times 6 roots of 6 minus 1/12 times 2 roots of 2. So another way to write this would be half root 6 minus 6th root of 2. And then finally, if we wanted to get a common denominator and write this as just a singular expression, we can now write this as 3 roots of 6 minus roots of 2 divided by 6. That would probably be the cleanest answer that you can get. It's probably the one that that you would probably see in any traditional back of the book type of answer. So before we go into the next problem, go back through, make sure you understand the process, and also understand the origins of this type of surface area.